point for Chapter 1. Chapter 1 in textbooks is always a history of computers, stuff like that. And so we're going to see if there's anything useful to glean out of it. Because you never know. So what is an algorithm? Now we're back in fundamentals of programming. Just a recipe. It's a recipe for solving a problem, right? Just like you have a problem that you need to bake a cake, you get a recipe for that. You need to subtract two numbers. So, algorithm for subtracting two numbers. You write down the numbers with the larger number above the smaller one. You align the columns on the right. You subtract one from that one, borrowing as need be, and to keep going, right? So, the act of programming is just the art of taking an algorithm that you have mentally or that you've written on paper and encoding it. Coding doesn't mean, hiding it in a secret cipher. It just means translating from one to the other. So, features of an algorithm: a finite number of instructions. Each individual instruction should be well defined. The action described by the instruction can be performed effectively or be executed by a computing agent. It describes a process that eventually halts. You want your program to eventually end, and solves a general class of problems. Computers can be designed to run a small set of algorithms for performing special tasks. So, our general background terms: information is commonly referred to as data. I always say data, but I guess that's because I watch too much Star Trek. In carrying out the instructions of an algorithm, the computing agent manipulates information. Usually, here's the flow that we're going to do. We start with some input, we transform the input somehow, and then we produce output. Even games follow that kind of sequence, right? The input is the movement of your joystick or whatever, and then it's processing that input, and then it's displaying the output. It just happens to be looping, incredibly fast, 100 times a second or whatever, in order to gather all that data and update the position of everything on the screen. So a lot of the programs we write will follow that general flow, right? Enter your height and weight and name, and then we do something, we do something, we do something. Here are the results. Or, how many pounds of sugar are you buying? You type it in. That is worth this many calories. That kind of thing, right? There's always the input, there's always the processing, and then there's always the output. You could just write a program that did input only, but when you were done inputting it, then why would you have written the program? If it did output only, it's kind of like a screensaver, right? It's fun to look at, but you're probably not going to do much with it. And like I said, they always go into the the history of computers or whatever. We know what hardware is. Hardware is the stuff you can touch, the physical devices. The software is the stuff that you install on the hardware, the programs. And in this particular case, our programs are supporting programming languages. And by the way, you can take Python and wrap it up into an executable so that you could just send somebody that executable. And I've had somebody ask that we covered that this semester, so we will figure out how to do that. Because otherwise, if you send somebody a Python script, if they don't have Python, they're not going to be able to use your program. Alrighty. How many people didn't know what an input device is? An input device is what you give input into the computer. The keyboard, the mouse, the thermostat that's attached to the engine, the accelerometer in your phone, so it knows if it's being dropped or so that your Pokemon Go can go. Your output device. Well, nowadays the input and the output devices are quite often the same thing. They're the screen touch input. Kind of cool. Our devices now look, kind of magical. They look like the stuff that, Star Trek Next Generation thought they would look like in the 1980s with the touchpads, except ours are much more awesome and thin and sleek and cool. So then they're coming out with those wacky bending ones. I'm not sure how I feel about the foldable phones, but might be cool. We know what memory is. Really, there's two kinds of memory that you get concerned about. One is, the RAM, the stuff that you load your programs into. And the RAM is what gets reset every time you turn off your computer. And then there's the semi-permanent kind of storage, the hard drives, although nowadays lots of machines don't have hard drives. Your phones and your tablets don't. Instead, they store it to a sort of flash RAM. But at least it maintains its state when it's powered off, right? Otherwise, you'd have to reinstall your phone every time you shut your phone off, and that would be a drag. So you still have those two distinctions. So when you buy a phone, you usually buy it, say, looking at the number of gigabytes of permanent storage it's got. I want a 64 gigabyte phone or whatever, but it's also got a certain amount of RAM in it. Surprisingly low compared to the monstrous amount of RAM that we put into our laptops and our desktops. So data is stored inside the computer as patterns of binary digits, zeros or ones. Everything boils down to zeros or ones because that's an absence of electricity or the presence of electricity. And yeah, you could come up with some wacky scheme where a certain amount of electricity, between the two meant a certain thing, but generally, on and off. And computers were invented even before semiconductors were, using electronic relays. And if the relay was open, power could not go through it. If the relay was closed, then power could go through it, and that was a one. And even before that one, you had the purely mechanical ones with the gears and stuff like that. But that's a bit different. So we will talk about bits and bytes just a little bit because that's more fundamental stuff. And I know that some of y'all haven't had the fundamentals, but I don't want to go into that because it's not so pertinent to what we're talking about in scripting. But here's our model of a computer memory. We have chunks of, if we count them, it looks like there's going to be 16 bits per cell. Typically, memory is conceptually grouped as 8 bits per byte. Whoever, was developing the architecture of the Intel chips or whatever in the very, very early 70s picked that. Did I see a hand raised? Yes, sir.
Yes, sir. Are you recording the lecture?
Oh, I hope so. Yes, I am. Thank you so much. Thank you so much. All righty. So, this looks like they have decided that there's going to be 2 bytes per cell. Whatever. So we can see that we have a memory address here, and then there's an additional one, and there's an additional one, and then there's an additional one, and your machines here probably have 2 or 4 gigabytes of RAM on them. Your home machines probably have a lot more than that. Typically, they're clustered in groups of 8 or 16. Numeric data takes more in order to hold precise numbers. They usually nowadays use 32 bits to hold a single number. The clusters of 8 bits to make a byte is one way that text is stored. There are several different ways that text is encoded on your computer, but one of the most common ones is called ASCII, American Standard Coding Information Interchange, something like that. It's an 8-bit character set. It was actually 7 bits when it was invented, but 7 bits happens to fit into 8, right? If you have 8 blocks, you can use 7 of them. And when you have your bits and your bytes, if you have 1 bit, it's only got 2 states, right? It's either on or off. If you have 2 bits, it's got 4 states. I'm not going to do this for each one of them, but you could have that, right? 4 different states if you have 2 bits. 3 bits, 2 bits, 4 bits, 6 bits at all. 3 bits, 8. Now we see the pattern already, right? So 4 is going to have how many different states? Yeah. 5 is going to have 32. 6 is going to have 64. Technically what it is it's 2 to the power of x. And by the way, forget that symbol because that doesn't work in Python. For exponents, we're going to be using that symbol. Now, if we were going to encode the English alphabet in some punctuation, 6 bits would be enough if we only wanted uppercase. But by the time you want lowercase, you're adding 26 more, so you have to have 52 characters just for the letters. And then for the numbers, that would be 62. And then you'd only have space for 2 punctuation, right? So instead, you would want 7 bits. And that would hold, the entirety of the standard, American keyboard. with plenty of room for extra control characters, like control characters for, moving a cursor around or ringing a bell, and stuff like that. A lot of these things were invented before the adoption of computers. You saw the old black and white movies where Cary Grant's looking at a teletype or something like that, a stream of... They had to communicate this stuff by phone. The phones were sending data down in the form of bits way before anybody knew what any of this stuff meant. The devices had to be programmed to do it, and so they had to have the control codes. That would mean, okay, this is the start of the communication, and this is an A, and this is a B, and so forth. Anyway, so that's enough, but there are 8 bits in a byte, and a byte is the smallest unit of accessible RAM, in our computers, and so that gives you 256 characters. So if you Google up a chart, ASCII chart, they typically, that one looks really old and cryptic. I don't want that one. That one looks the same. Here we go, ASCII table, something like this. We can see that they've mapped out everything all the way up from, a 0 meaning whatever. The characters, here's what they are. Like hitting backspace is going to generate a specific series of bits, and hitting the tab key is going to do that. And we see a whole bunch of stuff for the kind of things that, would work like for teletypes or terminals hooked up to a mainframe or whatever, acknowledgments and pressing the shift key and disabling the shift key and stuff like that. No, anyways, and then we finally get down at 32, the stuff that we care about, the keys on the keyboard, the space, the exclamation mark, the double quote and stuff like that, all of our common punctuation. And I won't say all of our common punctuation because for some reason they stuffed a whole lot of it here for characters, ASCII codes 40 all the way up to, and then they kicked in with the numbers, and then they threw in some more punctuation, and then they chose the letters, and once the letters are done, they threw in some more punctuation, and then they threw in the lowercase letters, and just to top it off, why not throw in some more punctuation at the end? But sort of kind of makes sense. They did choose the position of the letters with forethought, I guess, and because at least they're all contiguous, and that wasn't necessarily the case. IBM had their own encoding system before ASCII was invented, which they used for a long time, called EBCDIC or I don't know what the letters are, whereas the letters are not contiguously allocated in the, there were gaps in the numbers. So if you were looking at character number 41, it might be a B, 42 might be a C, but then you might have to get to 46 or 47 or something like that to get to a D. So this is plain text. This is ASCII. This is what gets created if you create something like, open up Notepad or whatever. It's a 8-bit character set. But 8 bits is not enough to hold every letter in the world, right? The problem used to be, the Russians, using the internet would not be so pleased as to be restricted to our alphabet. And there's really no room to put their character set in it. So you would use the extended character sets, numbers past 127, because we could go all the way out to 256 values. So there's plenty of room to put all the Russian characters in there. But then, German and French and Italian, they all needed their own custom character sets. And so if you viewed a Russian web page, in the 90s before Unicode became common, then it would look like complete gibberish, because you would not be using a font that had those characters that was mapped to those specific positions on their extended ASCII. So you would have to choose your encoding. Some of y'all may remember that browsers had a place where you could pick which encoding you wanted to view the web page, and until you did that, it looked like gibberish, right, if it was a non-English web page. And then once you chose Russian, if you went to a French website, it would look like gibberish until you chose the encoding for that. So when we write a program, what's going on in general is that we write it in some kind of English text. and we save it, and it's probably going to be saved as ordinary ASCII. And I skipped something I was just about to talk about. ASCII is for the plain text, the stuff that Notepad can enter, but it's generally only good for English. And so to support other languages, Korean, Chinese, things with massive numbers of letters or whatever, you needed more than 128 or even 256 characters. If memory comes clustered in groups of 8 bits, if you choose 16 bits, it turns out that you have a really large number of characters that you can support. 2 to the power of 16. I believe that's 6,65536, something like that. That'll support a whole bunch of alphabets. Characters, character sets, for just about every imaginable language. And even emoji are being added to the Unicode standard now. So that's called a multi-byte character set, of which Unicode is a multi-byte character set. I think it can even be extended so that you can use more than 2 bytes per character for whatever. I don't know if they need to add Klingon or Elvish or something to it. Maybe they'll expand it a little bit more someday. So a multi-byte character set is supposed to have every character, on the planet, right? And every time somebody decides that, you need an emoji of somebody, giving a peace sign with different skin tones or whatever, then those get shoehorned into the Unicode standard as well. But the simple text editors and the programming tools and stuff like that tend to just support regular ASCII. And it's kind of weird to think that the Japanese programmers are writing using English, right? They learn, what print and input, go to, and all those words mean. They're kind of learning English just in order to do this, just because the vast majority of computer development originally, in the 70s and stuff like that, was done in England and in the United States. And so I don't know of very many, like Russian-specific, and when I say very many, I don't know of any, Russian-specific programming languages. I'm sure that they were invented because the Russians had their own, encoding set. They had their own hardware and stuff like that during the Cold War. People didn't sell computers with them. They certainly had their computers. One thing they did was, get other people's computers, and reverse engineer them and make their clones, and then at that point they would be adopting, the standards that everybody else did. So, your Japanese programmers are probably programming in English, and they still only need an 8-bit character set. So what you typically do in programming is you create what's known as a source code file. The source code file is plain English-looking text. Now, of course, they could use variable names and function names. Those are the things that you pick, right? Those aren't built into the language. If I want to store my weight into the program, I would create a variable to hold it. And so variable names are the things we pick, and I could make one called weight. I could, abbreviate it if I'm lazy and just call it WT. I could be really lame and call it W. I think I've said it before, maybe not. Single letter variable names are incredibly lame, yet I'm probably going to be doing them anyways, because the longer I make the variable names, the more typos there are going to be. Right, and then the longer it takes, for everybody to get together. So it's a balancing act. Sometimes I don't always show best practices because I'm making it the easiest to type. You should not be making your programs easiest to type. You should be making your programs easiest to read and for somebody else to come up and understand what it's doing. So weight is a great one, but it's not the best possible variable name. What might I want to know about what kind of information that weight variable is holding? If you say somebody weighs, 65, does that mean that they weigh 65 pounds? 65 kilograms? 65 is pretty low, that's so it probably doesn't mean pounds unless you're talking about kids. Kilograms is a more reasonable guess. So you might want to put the units, right? Weight in kilograms, right? Weight in pounds, weight in ounces, stuff like that. Now, you don't have to go overboard, right? Patient weight as measured in pounds is equal to, 156. Yeah, you could do that. Are you going to want to type that every single time you need it? No, of course not. Your goal is to make your code readable, understandable, so that somebody else or you looking at it later can understand it, but you don't need to go overboard. You'll see a scheme that I'm following, which is a lowercase letter, beginning with a lowercase letter and then a whole bunch of lowercase letters, but then when we create a new word, we start it with an uppercase letter. And then we separate our words like that. That's not the only way to do it. You could do it like this. Why not do it in all caps? Well, this used to be an incredibly common way of doing it. If you saw code written in the 70s, it would look like that. At one time, some programming languages decided that all of the computer commands would be in lowercase, and anything you typed in uppercase was a variable name, and you couldn't mix them. So, back those programmers would use something like that. This is considered pretty much the standard recommended style now. So when you're creating variable names, I'm not going to ever count you off for, putting uppercase letters at the beginning of your variables or stuff like that. But in general, this is a style that if you show somebody else your code, they're going to think you're a professional programmer if you follow. And this is what's known as camel case, because it's got humps in it, right? Honestly, a lot of the time, well, because I'm old and I learned programming like that, I like the way underscores look. I kind of like that a lot. And when I'm typing stuff up here, again, I'm trying to make it easier for y'all to type. And if I put in speed of light, and then y'all type it, somebody's going to type it like this, speed of light, lowercase o. Somebody's going to type it like this, speed of light, right? So, again, I don't always do that. I don't always demonstrate it just because I try to pick things that are easy to pick, to type. But just tuck away in your head that that's the cool way of doing it. That's the professional way of doing it, but that works just as well. And very occasionally I use uppercase variable names just to kind of bring them out, but also because lowercase l, uppercase I, and 1 look all very similar. And so when I'm typing code in up here, I can come up with things that kind of look ambiguous. And if I notice those ahead of time, I will either try to rename it or I'll try to use uppercase. That is real clear. Even the folk in the back of the room are probably going to be able to know that that's an L and not a 1 or something like that. So again, I don't always follow best practices when demonstrating stuff. But you can do better than me when you write your own programs. The reason single letter variable names are for the birds is just that you don't know what it means. If you're seeing a page full of code and you're seeing X is equal to input, from device driver D, whatever, you go, I don't even know what's going on. I don't know what it's reading. I don't know what this is. But if it said number of bytes, right, is equal to input from, device driver, D, something like that, then you know a lot about what's going on just based on the names, the variable names. This is useful information. The computer doesn't care. I could call this Frodo, and I could call this Tony Stark. It'd be stupid, but I could, as long as later on I use that same variable name, right? Create file, of Frodo size, right? I've had, I took classes with students who, were weird and they tried to create, fantasy stories with their programs by using, character names rather than variables. And, they're probably making $1 million because they're really weird and I'm not. But anyways, so variable names are just important to us, but they are important. And again, I will use single letter variable names up here just because they're easy to type. And when I'm demonstrating a loop, it's easier for me to type this. For I in range, 1, 10, rather than typing for, numeric counter. And especially if I'm having y'all type, I'm probably going to do that, right? There are some happy mediums, though, right? If I'm talking about some kind of character, in a name or something like that, I might, do for CH in name, right? CH standing for character, right? C is a little bit too ambiguous. You don't really know what C might be. But you'll see me use I. I is almost always an index counter of some kind. It's going to be an integer. I'm probably never going to use I for any other purposes. You don't have to memorize these. You're just going to see them over and over. You'll see me use, X for the same kind of thing. There are specific differences between what an index counter is and what a numeric value is, and I'll talk about that. And you may very well see me use CH, but I'd rather type letter because it's not that hard to type in letter, right? And this is even clearer, right? For letter in name. Do that. And by the way, why don't we go ahead and figure out what this statement is doing here, because I'm showing you all sorts of stuff here. I was making some of it up off the top of my head. That's not going to work. I mean, yeah, we could kind of make something like that, but there's certainly no create file command that took a number of bytes. I just made that up totally off the top of my head. But these are actual statements in our particular language, of course, of choice. They don't have to be written that way. If we were programming in a C or a Java language or something like that, this would look something more like this. For integer I equals 1, I is less than or equal to 10, I plus equals 1. Or actually, those cool kids would use plus plus, meaning add 1 to I each time. Our language doesn't support plus plus, so if you've seen that in a language before, C++, right, we're going to always use plus equals 1. I plus equals 1 is a shortcut for I equals I plus 1. And I got into a dumb state where I had a textbook that never demonstrated this for some reason. And all of my code examples and my quizzes and stuff like that just relied upon that. And until I realized that the textbook, did not show that, I wasn't even calling it out, specifically. Oh, by the way, guys, pay attention to this, because I assumed that this is obvious. All I had to do is say it once, and that it would, people would understand what it meant. And it was never mentioned in the textbook, and some people were taking it online, and they probably weren't even watching the videos, and they had no idea why my test questions were written like that or what was going on. So this just means add 1 to I and store the results back into I. Now there's something very specific about the syntax that we're seeing here. When we see something like this, x is equal to x plus 1, that does not mean the same thing as this. If we were physics majors, or whatever, we're used to the idea that, we could write the equation either way, and it makes sense, and you could do whatever transformations to the equation you needed to do in order to get, to isolate the variable of choice. No, this will not work in our language. And so if I ask you to write a line of code that will add 10 to a number and store it in another variable, if you wrote it like this, that would be an incorrect answer. If you put that into your program, it won't work. You have to use the left-hand side for storing the variable, and the right-hand side is the expression. So this is an expression. This is a variable. The expression gets evaluated, and the results then get copied across the equal sign into the variable. So you can do this, name equals Fred, but you can't do this, Fred equals name. They look the same to us, but the people who invent the programming languages define a syntax, and I've never seen one that accepts that. So just know that if you get a weird syntax error, that's one of the things you're going to have to look for. Hopefully the message that the compiler, I keep missing a topic because I'm not following the PowerPoint very closely because I think it's boring, is, wow, I totally lost my train of thought. We're going to open up idle and type in a couple of these for loops just because we want to see what they do. And you guys probably remember folk who've taken 1113. On the other hand, there are some folk in here who took 1113 with instructors who never taught a programming language. Not that they'd never taught a programming language in their life, they didn't use a programming language to teach the class, right? And some of y'all may have taken it with JavaScript and stuff like that. So I'm going to go to the search box, I'm going to type idle, I never remembered to dock it, apparently, in the taskbar or whatever. Oh, and let's pretend that we're Windows gurus, and I'm going to show you something. You don't have to go to the search box if you know the exact name of the program you want to run. You see the Windows key between Control and Alt? If you want to run a program, you can hold Windows and then hit R, and it'll ask you. And at that point, you can type in idle. No, you can't. Forget that. Some things work there. I could type in CMD, and it would launch the command processor. Okay, so here I was showing off, and then I looked pretty lame. All right, so what I did is, like I said, never start entering stuff where you see the brace, brace, brace. I think I said that before. And sometimes, like if a student missed me saying that, and I've typed in 30 lines of code here, and they've in my program after doing file new, and they're typing in the 30 lines here, they're going to get very frustrated. It's doing different things there than it does when I'm typing there. It's executing all the commands instantly. Their program might still possibly work if they're a 100% accurate typist and I don't change the code, because you can't go back and edit when you're just entering commands into the shell. So we're always, as a matter of course, unless I make it very specific otherwise, we're always going to do a file new. All right, I'm going to do a save as. This is the second lecture, so I think I'll call it lecture B. Or maybe just B. B.py, although I didn't need to add the extension, it would have added it for me automatically. Alright, so here we're going to go. Lower is equal to 10. Upper is equal to 20. For x in range, lower comma upper. Print x. That looks like it would print 10 to 20. I bet somebody remembers what it's actually going to print. Somebody hazard a guess. I just said it's not going to print 10 to 20. It's going to print 10 to something. It's going to go up to 19. Because this is not defined as the upper point. It's one less than the upper point. Once it hits the upper point, it exits the loop. So this is actually going to print 1 to 19. And when we run it, we'll see that to be the case. If you're going to start at 0, you don't have to put a lower range. It will assume that if there's only one parameter, the parameters are the things between the parentheses. So it will look like this. For x in range, upper, since I did not give it 2 parameters, it's going to assume that the lower is equal to 0, which means it's going to count from 0 to 19. What if you don't want to count by ones? You can add a third number and tell it how much to add or how much to subtract. So like if we wanted to count from 20 down, well, let's do a simple example first before we start getting all negative. For x in range, lower up to upper, but stopping one less than upper, right, by 2's. Print x. So it's going to start at lower. What's our value of lower?
10.
Yeah, so we're going to do 10, 12, 14, 16, 18. And again, as I said, the for structure in this particular language kills the loop. Once it hits the upper, it doesn't let it execute the upper. So it would only get up to 18, because when it added 2 more to it, to 20, it would exit the loop. This is an example of looping. Looping is repeating a set of instructions until a condition is met. You can have while loops, you can have for loops. Some languages have do loops, do while. Some have do until. All we have are while and for loops, but those are good enough. You can pretty much do anything with those that you could do with all the other kinds of loops that other languages give us. I'm going to go back up here and add a comment showing the syntax for this loop in another language. I think I did that in my notes already. But this is the same thing as this syntax, and you don't have to add this comment. For x is equal to lower, semicolon, x, we're going to keep repeating while x is less than upper, x plus plus. Right. That's the syntax for that kind of thing. And those languages might use semicolons to mark off blocks of code. I like semicolons. Python doesn't, not semicolons. Curly braces. I say semicolons, and you're probably waiting for me to actually put some up there, and you think I'm crazy. So, you know, they may not have a print command, but anyways, you know, let's pretend that there's a print function in those languages as well. You see that this is x less than upper, rather than x less than equal upper. That's why it stops when it gets to 20, rather than including 20 in its range. People in other programming languages tend to do this. They tend to write it x less than or equal to the variable. We just have to remember that we're specifying one past the number. That's about enough belaboring on that point. So looping is repeating. And again, you don't have to type in my comments. I always upload these notes at the end of class. Repeating a section, which I'm going to rename block of statements, until a condition is no longer true. There are other kinds of loops. There are while loops. We could rewrite this loop as a while loop, but it would take more statements. X equals lower, and then while x is less than upper. All right. This is a difference between stating text and writing it, is I always do that. I say is less, but that's not correct syntax. I should say while x less than upper. So unfortunately, sometimes I glitch like that, and sometimes people are listening rather than watching what I type, right? Because it's reasonable. You know, you're looking at your keyboard if you're not a touch typist. And it's hard to be a touch typist when we're throwing in all these symbols. I certainly would not remember where, a star and a % sign was just by touch typing, even though I am a good touch typist. Anyways, print x plus equals 1. This is the same as this loop way up here. Oh, and by the way, when I get down on the bottom part of the screen, I know that it's hard for those of y'all in the back to see the bottom part of the screen. Remind me if I forget. I try not to scroll too fast because sometimes people are behind me. And by the way, if I'm getting too far ahead of you, please slow me down. Please, please. I know that I get excited and I type too quickly. Is the same as, that. Whoopsie. All right. There we go. This also loops from 1 to 19, assuming that lower is set to 1 and upper is set to 20. Now, I've typed more than a page full of code without testing it. That's kind of dumb. Normally, I like typing like 5 lines and then running it, and 5 lines and then running it, because I want to smoke out the syntax errors early. And it gives y'all a chance to do the same. So I'm going to do run module, and it happened to work. It spit out a series of numbers, and that's kind of, hard to interpret it because we haven't put any words on the screen to indicate what those numbers mean, but that's okay. This is what's known as a block of code. In this particular language, blocks of code are denoted by tabs. Now, I like the languages where you denoted them by curly braces. But that's a specific style of syntax that was invented with the C programming language in 1970. And it didn't have to be like that. Some earlier languages might have had, like, begin there and end there, or they had, for there and then end for there. It didn't have to be that way. Whoever invented these languages got to choose, the syntax. I certainly love the braces. Those languages tend not to care about tabbing. You could write your code like that, and it would work. You could write your code like this, and it would work. You could write your code like that. You could go crazy. It makes it harder to read, but it was legal code. Python, supposedly being the easier syntax, is more particular. Maybe that's not so much easier. You have to tab things correctly in this language, or it won't work. And that will come to bite us when we're typing in code. And it's not because y'all are dumb. It bites me as well. For example, say I want to do something, and then I want to print the result at the very end. Right? And so I would do print X there. Now don't do that. I'm going to delete it. That means run this block of code as long as this condition, and then print it out at the end. Who wants to have a guess as to what X would? If I run this, what's going to be the last thing I see on the screen? We've kind of said over and over that upper is equal to 20, and so X loops from 1 to 19. Is it going to be 19 when it gets here? Or is it going to be 20? It is going to be 20 because that's the exit condition. When it hits upper, it exits at that point. And so that would be 20. But what if I had that? It's going to print X every single time. Now that's a harmless mistake. What I mean by harmless is you would notice it really quickly. You would wonder why it was printing all that stuff, and you would probably do that. But there's another statement called a return statement. A return statement bails out of the particular block of code that you're working on. And if we had a return statement there, it would do this loop. It would print out all the numbers between, 10 and 20, whatever it was supposed to do, and then it would return. That would cause it to return after just printing out one number. And that might drive you crazy trying to figure out what was wrong. And eventually, you're going to have to raise your hand and come and ask me for help on that. And it's just because it's a matter of tabbing. Those languages with the semicolons, you never get that mistake. Yeah.
With the white space even this, can we use tabs or is it like triple or quadruple spaces?
I use tabs. You can use spaces, but you better use the same each time.
Yeah, I know some syntax, sometimes people care, sometimes they don't.
Right. So are tabs and spaces equivalent? They are, but they're not. If I do this, let me get rid of that return statement. I'm just going to copy this code here, and I'm going to paste it, but I'm going to make one of the lines spaces and one of the line a tab. And I'm probably going to get yelled at. I don't think that this is going to run. I think it will well, what do you know? Make a liar out of me. How did it know that, though? Right? Because that's certainly not going to work. I thought I'd seen problems when you mix tabs and spaces, but apparently Python is assuming 4. Yeah, apparently Python is assuming 4 tabs per space. I thought that was something you can configure.
As long, you can have it set where, at least I know in Notepad you can have it set where a tab equals X amount of spaces. If you have the same number of spaces in there as the tab equals, then it registers the same thing.
Yeah, okay, and you can set that.
They're lined up properly.
Yeah, you can set that in the editor, right? When I loaded up configure idle,
5 spaces.
I could say I really want
I think that's what
a tab to be 5 spaces, but it warns me that the Python standard is 4 spaces. So, yeah, you can mix them, but you ought to use one or the other. And the languages that use the curly braces do not care. Did your question get answered? Okay, that's cool.
I was just wondering about our last class because he was having trouble with it like that.
McWaters, his was giving him errors left and right when he when he was mixing them.
Oh, yeah, yeah. Well, if your editor wasn't hardwired to absolutely do 4, then I could see you getting into trouble. I kept starting to say this. This is the 4th time I've started to say this. Coding. You create a text file with the commands of the program. That's step 1. In some languages, there's a step 2, which is compile the language to make an exe, and then you ship that exe off to the person who's going to run it, right? Whether it's yourself or whatever, and then 3, they can run the executable. This language doesn't work like that. This language is an interpreted language, meaning it does it on the fly. You have to have the source code for the program in order to get it to run. You can't just give somebody an executable. Now, at the very beginning, I said that there's a way to turn a Python script into an executable, but that's a special circumstance. What happens when we do this is that we create our text file with commands in the programming language, and then when we want to run it, what happens is on the fly, the program file is read and then converted into a form that the Python interpreter can run. So line by line it is run. It's an interpreted language, so it's being turned into machine language. Machine language just being, what runs that particular processor, line by line. But there is an intermediate step. It does a syntax check as it's building the machine language for it to run line by line, which is how it catches errors like, why do I have all that gray up there at the top? It's interesting. Anyways, so if I had a tab wrong and I ran it, it might not pick that up until runtime, but that's a blatant enough syntax error that it didn't even let it run at all. So it's a good thing for a programming language, even an interpreted one, to do a sanity check on it, because you don't want to sit there and enter, census data for 27 minutes and then have your program crash before it saves it because of a syntax error, a missing, plus sign or something like that. So it's good for us that it does a sanity check and catches them. But does it catch everything? Nah, of course not. So it does, a syntax check at that point. Maybe that's step 3. And then at step 4, the machine turned into machine language, which is then, run through the Python interpreter. The interpreter is what makes this a multi-platform language. Y'all are probably used to the idea now of emulators, right? You want to play Nintendo games on your Android phone. You install an emulator that will take the binary bits and bytes of an old cartridge, but saved as a file that you can load on your Android phone. And it has all the software in it that mimics the hardware of the old Nintendo, right? So that's called emulation. Well, the Python is not emulating anything, right? It's not acting like anything else, but it does the same thing. You can have a Python interpreter on Windows and a Python interpreter on Linux and a Python interpreter on the Mac, and they're written completely differently behind the scenes, right? Because those languages have dramatically, those platforms have dramatically different syntaxes and machine languages and stuff like that. But it lets us write the same code that'll run on all those different platforms, because it's up to the interpreter to turn it into machine language line by line, and then to run it through the Python. Did I spell that wrong? Interpreter. I guess that's right. So that's the advantage of an interpreted language, is that you can write an interpreter for every platform that you want to run it on. You could probably write, nowadays microwave ovens come with microprocessors and stuff like that, and they probably have some operating system hidden behind the scenes in order to do that. I don't know, but the devices nowadays are getting smarter and smarter, and your TiVo or your set-top box or whatever is a full-fledged computer, probably as powerful as the computers that you bought, a couple of years ago. And certainly something like an Apple TV or Roku or whatever is a full-fledged computer as powerful as your as your phones are and stuff like that. Why was I going off on that? Anyways, so you probably have an operating system on your microwave, and you could write a Python interpreter on it. And I've seen people, or I've seen, not people, but videos of people playing Doom on a printer LCD. Right, they took the Doom source code and they compiled it and they uploaded it to the operating system of the printer, and you use the little buttons to play Doom on your printer. And the only reason people do that is to prove that they can. Right, it's a way of showing off and being awesome. Alrighty, back to our exciting PowerPoint. The loader takes a set of machine languages as input and loads them into the appropriate memory locations. Now, our loader is actually part of the Python interpreter. Once we load the program, we have it in memory as the text file. That's not really the loader, but then it gets turned into machine language. So it's machine language is just all pure zeros and ones. If you load up a .exe file or something like that in some kind of editor, you're not going to see this code that we see in our Python language. System software, the computer's operating system, file systems, user interfaces, and then we have our applications. Now, these are actually both programs, right? If you run a formatting command or whatever, or you type in dir, or you have a window like that, that is also a program. This is Windows Explorer. And if I hated Windows Explorer, I could probably launch the task manager, find it running, and kill it, right? It is a process just like any other one. And then I'm stuck, right? I can't interact with Windows anymore. I ought to be able to get it going back again by doing File New and typing Explorer. I'm not going to do all that in case I get into an unworkable state. But they divvy up, you're right, just into categories. So your applications are your games and stuff like that. And then your utilities are the more single-purpose stuff for just interacting with the computer, but it's not a game or a productivity software, right? So a utility is something that you write in order to perform a specific smaller task, right? You might write a utility that opens up all the files in a directory and, prints them out, right? Just top to bottom. You want it to print out every file in that directory. I wouldn't call that an application so much as a utility, but honestly, an application is a utility, is a program. These names are just kind of chosen, right? Just like, everything is an animal, but then you have different kinds of animals. But then you could kind of get into arguments, about what kind of animal it is. Not really, the scientists are very precise about which phylum they go in, but then they argue about them too, This thing is, part of this phylum. No, it's not, it's part of this. And just like, birds were one time considered an entirely different branch. And nowadays people have decided that birds are descended from dinosaurs. And so they moved that entire branch under the dinosaur family tree. So scientists have developed high-level programming language. A high-level programming language are the ones that resemble English, because we don't want to write in zeros and ones. And there is an intermediate level between writing zeros and ones in a high-level language known as an assembly language. An assembly language has just a series of mnemonics. And this means subtract whatever is in register AX on your computer from BX or vice versa. I don't know. But there's a specific machine code, right? And it's the machine code that is very platform specific, right? Intel processors follow one machine code, but the ARM processors in your phone or whatever follow a different machine code or whatever. So this is assembly because, originally people programmed in machine code, or they more realistically, they didn't type ones and zeros. they treated these as numbers, and they would have typed in, you know, a number that represented that and a number that represented that, and they got turned into those zeros and ones. But we don't want to do that. We don't want to do that. So the high-level languages are the ones that have the English words in them, for, you know, and while and stuff like that. And algebraic syntax is important to us. I wouldn't want to have to write sub AX, BX, and then, you know, add, you know, something, something, when I could type A equals B plus C, right? We like that algebraic notation. So start by writing a high-level. That's our text file containing our Python code. And then we run it, and it translates it. It does a sanity check, checks for syntax errors. If no errors are found, it can be executed by the runtime system. Python is our runtime system, the Python interpreter. It might execute the program directly on the hardware, or it might be fed to an interpreter. And that's the way this works. If we have an executable, there's no layer between us and the operating system. Right, that's why your games run really fast, because you know they're written as an executable that runs on that specific platform, and there's no middleware. However, stuff like Java and Python require that middle layer to work, which means that they run a little bit slower, but they run on more platforms. And Python will run on any platform that has a Python interpreter created for it. So text editor, translator, runtime system. In the output from each, translator, a lot of people call that a compiler, can kick out error messages, or it can kick out the code that is sent to the runtime system. And the runtime system can kick out error messages as well, like what if your disk gets full, or you open a bad file name, that file doesn't exist, or you access a drive letter that doesn't exist, or something like that. So it can kick out error messages. Otherwise, it can do program output, and the user can be adding their input at that point. Ooh. This is obviously not intended for display on the screen. All right, in the 1700s and before that, algorithms. People learned, you know, that in order to calculate. Have you ever wondered how, you know, pi was calculated back, you know, by the Greeks or stuff like that? Well, I don't know how they did it, but something to the akin of, you know, having a whole bunch of small pebble counters or whatever, and you take a circle and you fill it with those pebbles, and then you measure, you know, around it somehow, a piece of twine or something, and then you can pick the ratio that would get you pi based on that, but it would not be very precise, right? But then there are mathematical algorithms for calculating pi. And so the first mechanical computers were built by Pascal and Leibniz, and we could Google up what they look like, but they're basically just brass boxes with dials, you know, 10 dials or whatever, and maybe some, you know, yeah, why don't we look up one of them? Of course, it comes up with the programming language named after the dude. Yeah, like that. Right, because by the 1800s and stuff like that, business was important enough that it was generating large numbers that were hard to manage, right? Like the East India Company, you know, funded the settlement of New York, or they called it, you know, New Amsterdam or whatever. Huge amounts of money for the time were starting to be generated. And so you had to be able to track them, right? And you had to be able to perform calculations on them. I expect this, you know, this state, this territory to generate this much tax. I need to be able to calculate a percentage of it or whatever. So you would put the stuff in a dial, and you would turn a crank, and you get some cool numbers that you could write down. So they weren't calculators. They were just mechanical calculators. Science, similarly, right? Measuring large distances and trying to figure out, you know, trajectories of the moon, and, you know, the differences between where the stars would look if you're on the northern hemisphere, and the, you know, so that you could create books where if you were looking with one of those cool, I forget what they're called, you know, the spy glasses that, you know, rotate on the semicircles, where the people on the ships could judge what longitude and latitude they were at by the positions of the stars. You know, they had to have books that went along with that. And creating those books was an incredibly tedious task. And if you had a calculator where you could type in a formula and crank it, write down that result, crank it again and write down that result, would be a lot better for creating a book with 1,000 numeric entries than if you had to do those by hand. And so libraries used to have big books full of references of, you know, all the logarithms of the numbers between 1 and 1,000,000. And some poor student at Cambridge or whatever had to, you know, write all the numbers in there. Of course, there were mistakes in them. So there were lots of motivations for creating devices. I'm going to kind of skip some of this stuff. But you can see that by the 1800s, people were inventing actual darn good real computers, but they kind of failed. They didn't have the technology to create the brass wheels to quite the preciseness required, but they invented the concepts which are still in use today of the information store, which is what we call, you know, RAM, and then, you know, the programming store, which is where we load our programs into, and then input and output. And the reason they were able to do a lot of that stuff is that people had already invented punch card machines, but they had done so for the weaving of textiles and stuff like that. But if we look up the Babbage Analytical Engine, you may remember that there used to be a store called Babbage's at the mall, you know. Not a great picture of it, but, you know, there we go. You know, it's purely mechanical. The dude invented it, had it designed, but his funding ran out, right? You know, because it, you know, cost overruns and stuff like that. But they even invented a programming language for it. The daughter of a famous poet at the time, oh my gosh, Ada Lovelace, you know, managed to bring up the name. She invented the programming language that would run this thing. And he invented the hardware for it. It just never worked. But it had all the components that you would consider a modern computer. Some of these things were, you know, the RAM, and it would read from the RAM and run the program, which you set by spinning the wheels and stuff like that, and it would produce the output in the form of, you know, whatever punch cards were being produced. But we like electronic computers. Electronic computers were invented in the 40s as part of the war efforts. And the Germans and the English and the Americans invented digital computers. The Germans' computer efforts were bombed out of existence, right? The Americans built them to, you know, create better weapons, nuclear weapons and, you know, trajectory tables and stuff like that. And the English invented computers in order to crack the German codes. First symbolic programming languages. The symbolic programming languages are the things where you have, you know, English-like words and they get turned into the machine language. And then instead of using vacuum tubes and mechanical relays, you get transistors, right? You know, far smaller pieces of logic so that you don't have to have, you know, room-sized computers, you know, ENIAC and UNIVAC and stuff like that, you know, in the 40s. Can you imagine trying to maintain a room full of vacuum tubes that had, you know, 5,000 vacuum tubes or whatever? It was a full-time job just running around replacing those vacuum tubes. All a vacuum tube is a light bulb, right? But it has very specific states that would represent a number. It could, you know, be set to 10 levels of brightness or something like that. All righty. The invention of the integrated circuit. The first mini computers, right? So you didn't have to have computers that were the size of a room. You could have a computer that's set in your room, right? Maybe it was just the size of a big copying machine or something like that. The emergence of the software industry, right? Because by the time people had mini computers, you know, you could have, you know, 1,000 Fortune, you know, 500 companies, you know, or 10,000 companies buying these computers, and it became profitable to create the software that they would buy and install on them. And then the first microcomputers, computers you can set on a desktop. And the graphical user interfaces as opposed to something that you just type into. And towards the end of the semester, we're going to be creating our own graphical user interfaces. And then the creation of networks, from the 70s, that actually started like before 1975. The first connection between, college campus computers was done like in 1970. And then the creation of the internet was pretty much, on a continuum between 70 and 80, but they didn't call it that at that time. It was called, ARPANET. It was run by ARPA, the Advanced Research. It was essentially run by the military, by the government. Okay. Skip. Worth reading. There might be quiz questions over it on the quiz. But y'all can read as well as I can, and I'm not going to say every word on these because I tend to say a lot of other words as well. I don't think we're going to do it, but it would have been kind of neat if we'd gone through the entire chapter in one day. Alrighty. Guido van Rossum, I think he's Dutch, invented the Python programming language. So it's a high-level, general-purpose programming language for solving problems on modern computer systems. It is an interpreted language. You can execute simple programs and statements on the shell, but the best way to program it is to create a program, right, which can then be rerun over and over and over. And so since idle is installed every time you install Python, that's probably the easiest way to do it. To quit, you can just quit the application with the close box, pressing Control-D. Well, I guess that's true on Windows. Not everything has uses a Control key. Macs have the Command key. So the shell is useful for experimenting with short expressions and statements, right? But really, what you're going to be doing all your programming in is a file rather than the shell. And we're going to stop there so that we can create a Dropbox for y'all to upload into. Alright, if you go to the assignments page, you'll see the Dropbox for B. If you took any notes, upload those. If you wrote the program, upload that. If you didn't, just create a little document that says I was here and upload that. I wish you could submit something that didn't even have to have an attachment, but you got to attach something to it. So I will open up the quiz for Chapter 1. It's not going to be due like next week or whatever, but you're going to want to read the chapter and the PowerPoint and then go take the quiz and then take it again because it is worth points, right? And so get 100 on it by taking it twice or whatever. The quiz will be listed or gotten to by going to Content and then hitting Cengage, and you'll see it listed here. You probably won't see a due date here, though. You're just going to have to remember to do it. And I'm sorry about that, but otherwise I have to set due dates and then I have to reset them so you can retake it, and then I have to keep resetting it. And I have to keep doing that to remind people to do it, but I'm expecting y'all to be grown-ups enough to do it that way. Okay, I just thought of a different way to handle that. But I'll make sure that there is a due date somewhere to prompt you to do it the first time. It's just not going to be a due date set in Cengage itself. And the reason that is important is that when you log into Cengage and you get all this stuff, if there's no due date assigned to it, people get tricked because there's a calendar mode, right? And if you look at the calendar mode and you don't see anything listed there, right, no activities done, people think they don't need to do anything. But that's not true. Don't rely on the calendar mode inside Cengage. Rely on the stuff that we're posting to D2L to tell you what to do. That makes sense? Don't not do this stuff just because you don't see an activity that says that it's due on week 2 or something like that. Alrighty, well, there's not going to be any further homework because we haven't really covered the programming language, so do make sure you get Python installed as soon as possible. And we will do more yummy stuff next week. Are there any questions so far?
You want us to just send the file that we did?
Yeah, if you created a file, go into Assignments, find the Dropbox for B, and upload it into there.
Do you want the Python or the code too?
The Python is the code.
One the file itself? Yeah, just this, or do you want it run as well?
Yeah, I don't care about screenshots. After last time, we're not doing screenshots for the lectures because that just takes too much time. So just upload the PY file. Yeah, you don't have to, pardon me.
To reiterate, you said quiz 1 as well as what we just did, right? I mean, no, for homework, it was install Python in quiz 1.
Right. I haven't set a due date for quiz 1, but I'll post the link to it and make sure that it's visible and easy to find.
Right?
Yeah. Yes, sir.
So one of these assignments says it's not like that.
Okay, so all you're gonna need to do is take a screenshot of it or something like that.
Oh, no, it's done through Cengage.
Yeah, all you have to do to prove that you installed Python is like take a screenshot of it and upload that. The only thing that gets weird is if you're not gonna install Python, in which case give me a note that says how you're gonna do your homework.
Quizzes aren't through that.
You said you were on to look at the Notepad++.
Oh, yes.
Yeah, I'd like to see that. Let me stop the recorder.
Right there.